Good morning, and welcome to the workshop of Modern Natural Language Processing, NLP. I'd like to start with thanking the Computer Science and Engineering Department, and I also would like to thank Ariel and the team of graduate students in this department for organizing this workshop. Before I start, I'd like to say that I am very excited about this modern natural language processing workshop because it is about, I think it is about the most interesting branch of artificial intelligence. Artificial intelligence is succeeding, and natural language processing is the most exciting part because it allows us to communicate with AI in our languages, and it understands us and we understand it directly. And also with natural language processing, the AI is able to learn from our knowledge. It can read our chats, our emails, our Wikipedia, our books, and learn from human knowledge and be able to answer questions and innovate in various ways based on this knowledge and using natural languages like English and Arabic. This is a 4-hour workshop. It has 3 parts. I'll start with a fast introduction to natural language processing in general. Then I'm going to concentrate on transformer-based architectures, which are the architectures that are responsible of most of the success in modern natural language processing. Of course, transformers are used to build the large language models that we all admire. Then we'll move to the practical and hands-on part of this workshop, working with LLMs and hands-on exercises. I have 3 main exercises or labs. The first one is about text generation, then sentiment analysis, then translation. We're going to translate from English to Arabic. Text generation, we're going to use large language models to generate text like short stories or jokes. Sentiment analysis, we will find the sentiment of some sentences or comments, whether they are positive, neutral, or negative. And because this is 4-hour workshop, we're going to have 2 15-minute breaks in between. In some convenient time, I'm going to stop like 1/3 after the workshop. We'll take 15 minutes break and so on. This is a slide about me. I'm a visiting professor here. This is my 2nd year in the Computer Science and Engineering Department. I come from the University of Jordan. I've been there since 1993, and I have a PhD and master's degrees from University of Michigan. At that time, I concentrated on my graduate research was about scalable shared memory multiprocessors. But after I returned to Jordan, I switched to supporting the Arabic language, and my main research area now is natural language processing using deep learning. I also have long industrial experience, and I am proud that I am active IEEE volunteer. Now, this first topic is an introduction to large language models. I'm going to go very fast on these topics. This is just a simple introduction about NLP, introduction, evolution of NLP with time, core concepts in NLP, techniques and models used in NLP, key applications, then challenges and ethical considerations, future directions and emerging trends, resources. At the end, I'm going to point out to you very useful resources and how you can get started or be an expert in NLP and large language models. This is the definition of NLP. Is a field of artificial intelligence that enables computers to understand, interpret, and generate a human language, like Arabic or English. It's very important because NLP bridges human communication and machine understanding, facilitating user-friendly applications, like "Hi Siri, do this and that." Now, NLP has evolved after the early beginnings in the 1950s, maybe landmarked by Alan Turing's definition of the Turing machine or Turing test. The 1980s and 90s there were good progress in NLP using rule-based systems and corpora, but that progress was slow and very hard. You need to write the rules of languages which are very complicated. Then in the 1990s and the first part of this century, people started to use more and more machine learning and statistical approaches. And you know that recently, deep learning is very successful, and we currently use various types of neural networks. Now, we're in the age where we use deep learning and large language models to do very interesting things. There is continual advancement in this area. You can feel it month after month. You keep getting better and better application, better and better models, and more applications. Of course, there are always ethical and societal implications. AI will have and is having a great impact on all aspects of our life. And in conclusion, AI now and natural language processing are advancing very fast. They are providing opportunities that were not imagined before, and this success is expected to continue and keep changing our lives. Now, these are some of the core concepts in NLP. There is syntax, the structure of the language, and semantics, the meanings of the sentences and paragraphs. In NLP, usually we do, for the text tokenization, we break sentences and paragraphs into smaller words or tokens. And in many cases, we analyze these tokens or words by doing tagging for the part of speech, POS. Like I'm going to show, I'm going to show examples, but maybe when you say this is a boy, boy is a noun, and so on. Named entity recognition is to identify the names and what type of names we have in some sentence or paragraph. Dependency parsing analyze the grammatical structure to establish relationships between words. Here are examples. we usually enter text like this is good morning, Rosa. Good morning, Rosa is entered one character at a time. Now we can, this sequence of characters is usually split into tokens, like a one-word token. So we have here 3 tokens, good morning, Rosa. Part of speech tagging is you take each token and specify its type, like good is adjective, morning is singular noun, and so on. Syntax tree is higher level, and entity relationships. Now we've entered the semantics. Morning and good are related. Morning now knowledge base. Now we are trying to understand the meanings and the relationships. Morning is part of a day. Rosa is name of a person, and also she's female, and Rosa is an English name. Now, to summarize the history and the evolution, we've started with rule-based systems, early NLP methods based on hand-crafted rules. Experts, excellent programmers write these rules, and they are usually experts in the target language. Machine learning, as you know, involve algorithms that learn from data and make predictions or decisions from data. Deep learning use in neural networks to model complex language patterns, and currently transformers and pre-trained models were introduced, and like BERT and GPT, and they have revolutionized NLP tasks. You know that NLP has many applications. This is 5 classes of NLP applications for text classification, like categorizing data into predefined groups, like positive or negative, sport, economical, or other. Sentiment analysis, determining the sentiments. Sentiment analysis is some sort of text classification, but it's very important. Therefore, it is now it's listed here separately. Machine translation is important. You know, Google Translate, and with machine translation, we get automatic translation of text between languages. I think now Google Translate can translate among 200 languages. Question answering is important. Has many applications, like in customer support systems that can answer questions posed in natural language, like English question or Arabic question. Chatbots and virtual assistants are becoming more and more important. They're conversational agents for various applications. This is even a larger categorization of NLP applications. I'm not going to go, but here from type, like search, editing, dialogue writing, email, and some of the applications in each area. Now, although AI in general and NLP are succeeding, but they still face many challenges. Languages are difficult to work with because they carry ambiguity. Sometimes some word or some sentence may mean multiple meanings. I'm going to give later some example from Arabic poetry. When you take one verse at a time, you may not be able to understand it unless you take the entire context. Context understanding, ambiguity and context understanding are related, because when you don't know the context, you may not be able to discern the ambiguity in the text. Dealing with sarcasm, like his mouth is as large as a house. Now, no one has a mouth that is as large as a house, but this is sarcasm, and you need special AI in order to understand this is sarcasm and not reality, and must not take conclusions on such statements. Language diversity is important. Some people may think that when they understand Arabic, when they learn Arabic, like modern standard Arabic or Egyptian dialect, then they are fine. They can communicate in Arabic anywhere, but there are many dialects for the Arabic language, and even when you know one dialect or MSA, you may not be able to communicate effectively in other countries and other people. Ethical considerations are important. I'm going just to point out that you all know about bias and addressing bias. One very important, one very famous example, just saying I am from India and I am from Iraq. Okay, these two sentences were given to a sentiment analysis model, and just from these two sentences, one sentence was classified as positive and the second was classified as negative. So this is biased based on the training data that the model was exposed to, and India, I'm from India, was classified as positive, and I'm from Iraq was not. Privacy concerns, we train these models on huge data, and this huge data should not include private data, because the model can leak it. When it generates text, it may generate some private data. Social impact of automation, you know that when AI can do things, and it's doing many things better than us, then industries are going to fire people or not hire people and use AI instead. And for example, you know that there is great progress in autonomous driving, and it's expected within 5 to 10 years that 35 million professional drivers are going to lose their job. These are the future directions and emerging trends. I'm going to come back to them later, but the trend now is to build universal and adaptive architecture, an architecture that is deep, that's very powerful, but also with wide breadth, where it can handle multiple areas. Seamless multilingualism. I know that there are some large language models now that are trained on more than 100 languages. So for example, and you can, for example, communicate with ChatGPT using English or many other languages. And the great thing is that the knowledge these models learn from one language can be used to answer questions in other languages. Agentic AI integration, this is very important because the AI can do for you multiple steps that are complicated, and this definitely improves the efficiency of utilizing AI. Multimodal AI integration, the AI is becoming more and more able to handle the multiple models of text, images, videos, and so on. Now, I come to resources and getting started. There are many books, but I'm going to show you in the next slides 3 of my favorite books. People can learn many things from online courses on Coursera, edX, and so on. There are maybe, if not thousands, maybe if not millions, thousands of datasets that we can use to tune and develop language models. And there are available tools for learning efficient Python libraries like the NLTK, Spassy, TensorFlow, and of course, I'm not listing it here, but the transformer library from Hugging Face. We're going to use it later in this in this workshop. This is the first one. This is an excellent reference for natural language processing in action. It is relatively not old, but I like it for the general things related to and classical approaches in NLP. This is excellent if you're interested in modern NLP, then hands-on large language models by Al-A'mar and Grotendorst is great. It is a recent book, and it has many applications, and it's straight to the point, and it tells you about the best available libraries and techniques. I also like this reference very much, hands-on machine learning with scikit-learn and PyTorch. This is my favorite for teaching machine learning in general. Chiron has introduced early this year this version of his successful book, Hands-on Machine Learning, but he has moved from TensorFlow and Keras into PyTorch, acknowledging the rising importance of PyTorch compared to other deep learning libraries like Keras and TensorFlow. And now this is the summary of the first part of this workshop, which is about which is an introduction to NLP. I'm going to stop here and start the next one. But if you have any question or any comment, please go ahead. We have 19 online, and yes.
Maybe periods that we training on all type of data.
I did not hear your question.
Couldn't it be done by just training it on type of data, all that?
Yes. Now the question is about universal and adaptive architectures. Can we get this by training the model on diverse data? This is one way to do it, but also I'm going to show later slides about the current trends in developing state-of-the-art models, and we want to improve it not only by knowledge and retrieving knowledge and dealing with languages, but also we want AI with better and better mathematical and reasoning and planning skills. And for this, we need to train it using more advanced training techniques. Now it is about half hour. And now this second slide set is a little bit longer. The title here is Transformer-Based Architectures and Large Language Models. And you know that large language models are the core of the modern NLP, and they're responsible of much of the current success and magic we see in modern AI. I'd like to change something here so that what you see here is also what's seen on Zoom. Okay, great. In this part about large language models, I'm going to start with review of architectures. Maybe start from deep learning, moving to transformers and large language models. Then we come back again to the LLM trends. What's happening to LLMs? We know that they are becoming better and better, but there are trends that we can see now, and we're going to learn about these trends. Then this is something from my own experience. Arabic NLP applications. I'm going to present to you very fast some of the problems that I've addressed, and they're related to the Arabic language using deep learning and language models. And there will be a short conclusion at the end. Now, you all know about deep neural networks, and that they are neural networks with 2 or more hidden layers. So they have at least 4 layers. Some of the deep learning models are thousands of layers deep. And when they're that deep, there are many weights and biases in between. They are called parameters. And in the learning process, we need to find values for these parameters using machine learning training algorithm. And in order to succeed, we usually need huge data. The larger the model you have, the more data and examples you need to give it in order to succeed in training it. This was not possible before. Only in 2006, Jeffrey Hinton and his colleagues were able to successfully train a deep neural network. And deep neural networks are capable of end-to-end solution. Like here, this is from their paper, 2006 paper, given an image of a decimal digit, just from the image, without any features, the network should predict the digit, the class 1 of 10 of that, and the algorithm that was developed here in this paper is used all over deep learning and machine learning with some modifications and improvements. Now, dense networks are the vanilla type of neural networks. There is input layer, output layer, and hidden layers in between, but they're called dense because they have many connections, and every neuron in one layer is connected with all the neurons of the previous. This is very powerful, but and we have many applications for dense networks like this, but they are not efficient for some applications like computer vision or natural language processing and dealing with sequences and text. To address this problem, recurrent neural networks were introduced. They're similar to the dense networks, but so you can think of this is 1, 2, 3, 4, 3 RNN layers, but in addition to the input coming from the input or from one layer to the next, the output of every layer is used as an additional input to itself. So, and with an additional thing is that when we use them with sequences, time sequences or text, and we feed the sequence one symbol at a time, like this can be the first character, second character, or first word by the second word, and this happens at the first time step. This happens at the next time step, and each subsequent step takes the state or what was found in the previous. So when you give the sequence, the final answer you get here depends not only on the last token, but depends on all previous inputs. This is very powerful. I'm going to show you later some of the applications of RNNs, and you can get impressive results with recurrent neural networks, and you can do many sophisticated and you can solve many complex problems with NLPs, but they are slow. They're slow because you need to keep feeding your sequence, every sentence, you must feed it one token at a time. Now, you know about transformers. Transformers are very important. They're the core architecture used in modern large language models. And transformers were introduced by Google scientists in 2017. This is the original transformer. The original transformer has, this is one encoder module, and this is one decoder module. But you can have multiple encoder modules and multiple decoder modules. And the input is given here, and the objective is to maybe translate it to another representation. Like you may give it here the text in English, and you want to get it here in Arabic. The encoder modules keep processing the input until we reach some representation. You can call it a universal representation of the intertext. Then this universal representation of the intertext is used by the decoder to translate it to the second, the target language, like Arabic. And this is done by using multiple, each module has multiple components. There is the feed forward. This is like a dense network, like before. There is also add and normalization here and here, but the important thing is the attention modules. And the attention modules, no, before talking about the attention modules, I'm going to talk about the reason, from my understanding, why transformers are successful. They're successful because they're much more efficient and fast compared with recurrent neural networks. In recurrent neural networks, you've seen we introduce one symbol at a time, but transformers include positional encoding. Positional encoding, you input your input in parallel as not tokens, individual tokens, but as a sequence of tokens. And in order to not to forget the order, there is the positional encoding. And the positional encoding ensures that the position of every token is preserved as it goes through the encoder modules and decoder modules. Now we present one long sequence or input sequence at a time. And when you have powerful computing resources like GPU with thousands and thousands of computational units, then you have your individual inputs can be processed at the same time, concurrently using the available hardware resources, the available processing elements of a GPU or TPU or whatever. Now, once you have your input entered in parallel, there is the attention mechanism. And the attention mechanism take the raw input and keep processing it and finding the relationships between the words and keep improving their representation until we reach some point like the universal, I call it the universal representation, where the input is represented in very powerful and form that the machine can use to do useful things. Now, large language models are transformer-based. They're here, large language models. They're part of the deep learning techniques, and the deep learning techniques are part of the machine learning techniques, and the machine learning techniques are part of the AI techniques, but also LLMs are part of this important branch of AI, which is the NLP. They learn rich representations of languages. You give them the input, and they learn how to represent this input in very, very rich representation. Like every token is translated into a vector of thousands of real numbers to represent the various aspects of this work, like whether it is singular or plural, whether it is gender, male or female, and so on. Usually, they're pre-trained. They're pre-trained on large data sets. You download Wikipedia, you bring as many books as you can, and you train the raw large language model simply on this huge data. Then I'm going to talk later about the pre-training process, but then we fine-tune the large language models for certain tasks, like chatting, summarization, coding, and translation. Once you get a large language models properly trained, you can do zero-shot training. It's with zero shot, it can answer questions without any further training, or few shots. You give it an example. See this example. See, I want you to answer like these few examples. Now, large language models are not open, are based on transformer architecture, but we can classify them into three main classes or types. There are translational models. They include these are encoder-decoder architectures. There is encoder modules and decoder modules, and they are usually used for translation. There are representation models. They are encoder only, and there are generation models that are decoder only. And we're going to see examples. Let's start with translation models. These are similar to the original transformer architecture. You have multiple transformer encoder modules and multiple decoder modules. And you give it an input like I love llamas, and here it's trained to translate it into Dutch. So encoder-decoder are excellent in translation. Representation models are encoder only. We give it the input, and it keep processing it using encoder modules until we reach some useful and better representation of the inputs. So the input is here, and the most famous representation is BERT. This was introduced by Google scientists, and here you get contextualized word embeddings. We're going to use representation models in the lab later in this workshop. Generation models are very interesting. They are decoder only. So they are trained, you give them an input, and this input is like a seed, but this seed can be a question. So from this seed, the decoder modules can continue from this seed and, for example, answer the question. So they generate the text that they expect should come after this question, and you get your answer. And the most famous generation models are the GPT models from OpenAI. Here it's trained to to complete the sentence I love, and it's given I love, it's generating the answer or the completion, which is llamas. Yes. How many steps? Yes. I don't fully, sorry, I don't fully understand your question. Please repeat it. Yes, different levels for what? Which type? Any type. Okay. Encoder.
So, per day, how many times do you use factor encoder to make sure that the answer, because this time we are
Yeah. How many times? Yes. How many times we need to use these modules in order to get the right answer? The question is, it must be first trained on many examples. So it's trained on many examples using some self-supervised technique, like we put here a head to predict tokens. So we give it the input, maybe with some tokens hidden, and we train it to predict the hidden token. After many training examples, it learns how to represent the input in contextualized word embeddings that are useful for predicting the missing word. To predict the missing word, you need to understand the language and the context. So the model learns to translate the input into these embeddings, this representation that is useful for predicting such a hard thing like what's the missing word. Then we remove the output layer, and we only concentrate on these word embeddings because they are excellent representation of the sentence, and we can use them for many things. We're going to have some example later. You're welcome. Okay, now for these are famous large language models. You know the GPT from OpenAI. There are Llama modules from Meta, and there are important modules from Google. And one trend was they were getting larger and larger. But recently, there is some trend not to increase their size anymore, but to try to make them smarter and more efficient. Like DeepSeek with 37 billion active parameters at a time, it was able to compete with much larger models like GPT-4. Now, this is the introduction about the architectures of large language models. I'm moving now to trends. I like trends, and I keep thinking about trends, maybe because I'm old, and I like to see what has happened before and what's going to happen in the future. But there are many trends that we now observe about large language models. Bigger is not always better. Long context multimodal, open source versus closed source race, reasoning, alignment, and training paradigms, small on-device language models, retrieval augmented generation and grounded systems, agents, tools, and workflows, and safety, robustness, and regulation. I'm going to give one or more slide on each of these trends. Let's start with the first trend. The first trend is that bigger is not always better. Bigger is not always better. It used to be when companies succeeded in developing larger and larger models, these models became better and better. But now they're very large and very costly. Therefore, there is huge effort in not making them much larger, but more efficient. And there are multiple techniques like sparse or mixture of experts models that are hierarchical and include multiple experts, and you don't exercise all these experts at the same time. You exercise a subset of these experts depending on the problem. Distillation, pruning, and quantization. Here, you start with a large model, then you try to cut it down to make it smaller. Distillation is using one large model to efficiently teach a smaller model. Pruning, you cut out things that will not affect the accuracy very much. A quantization, instead of using long representations of large significance for the parameters, you use fewer and fewer bits. Test time compute deep multiple modes. With ChatGPT, for example, you can have a thinking mode that is slow and will take long time, but it can give you much better answers for complex tasks. And there are lighter modes where the model thinks for a shorter time and give you acceptable answers. This is a graph where we have models from many companies from 2002 to 2015 and beyond. The vertical axis is the MMLU score, which is a score of the goodness, or how good the model is. And you see, in general, models with time are getting better and better. In multitask language, let me hide this one. Okay. So, but also you see, for this is GPT model, and this is another model. Yes, GPT-3 is much smaller than GPT-4, but with time there are smaller models from the same company, from OpenAI. The size reflects the diameter of the circle, reflects the size in parameters. The second thing is long context multimodal. I'm using ChatGPT to develop Python scripts for doing advanced things. I'm doing something related to Arabic poetry, and I have data coming from multiple sources, and I'm using large language models. I'm using ChatGPT to generate script that sometimes is more than 600 lines long. So, and I have been opening the same chat session in ChatGPT for a month, and I keep building on that chat and giving it, telling it about the results and asking it to analyze it and to give me better scripts and so on. And it is remembering this long context of conversation. And this is a current trend for all models. Of course, they're multimodal. Like I have given ChatGPT a Word document, sample Word document that includes some poetry verses, and I asked it to generate a script that extract from multiple Word documents the poetry verses and put them in a convenient text. I'm going to show you this thing. This is log scale. So this is exponential increase. With time, models are accepting larger and larger context window. Now, the winner here is Llama 4, and it can take into consideration a context of more than 10 million tokens. 10 million tokens. This is many bucks. So, yeah, this is very, make them very important from very long history of chat, or you can give it multiple documents and it can process it all as one prompt. The third thing is that open source versus closed source. Yes, there are companies like Google and OpenAI that invest millions, if not billions of dollars to develop powerful large language models and provide services through these models. But also there are some large language models that are open source and we can use them. And some of them come from China. I'm coming back to this diagram once again. The circle is closed source, but the diamond, like the llama here, and these two models from DeepSeek, the Chinese model, are open source. So, and you see that they have very competitive performance. They're very powerful, yet they're available open source. You can download them, you can use them to do whatever you want. The fourth thing is reasoning, alignment, and training. Yeah, I'm coming back to your question. This is, we want large language models that not only do things like answering questions from the data that they've learned, but also to do more complicated things like reasoning, planning, and mathematics. And now there is better reasoning training algorithms, and this is improving with time. Like 2 years ago, the best technique to train a large language model so that this large language model becomes a chatbot was the reinforcement learning. So it generates and it gets feedback whether the generated thing is safe, is accurate, is good or not. With human feedback, sometimes humans inspect the results and give feedback to the model to improve its safety and accuracy. There are better techniques now, like direct preference optimization. And now we also get data not from the internet and normal resources, but there is also synthetic data. Large players develop synthetic data, and this synthetic data allows us to develop better models. This is about the training data size. Again, this is logarithmic scale, and you see that with time, models like GPT, Palm, this is the transformer model of 2017, and you see with time, they're using larger and larger training sets in an exponential growth. In fact, in general, models, the data sets used to train large language models double approximately, not every year, approximately every 6 months, 3.7 times every year. This is an interesting graph. You know that the digital content on the internet is increasing in exponentially. Double every 2 years. The digital content doubles every two years. This is exponential, okay? But this is logarithmic scale. The rate in which large language models use data, the data sets of large language models, is increasing in a larger rate, and it's expected that with time there will not be larger data to train future large language models on this large or great. For example, Llama 3 was trained on 15 trillion token. Now, we only want to run large language models on smaller devices like smartphones, and there is some progress in making powerful models small enough to effectively run on smaller computing devices. You know about the hallucination, the problem. Sometimes the answer is not grounded, not correct. I think that until now, models are not trained to say, I don't know. try to ask ChatGPT anything, and it will always try to give you an answer, and this answer sometimes may be nonsense. The one technique to reduce this hallucination is to do retrieval augmented generation. And in this type of generation, the model bases its answer on some data made available for that model. So you ask question, it goes to the target data set, and it answer. I know that IEEE use it. There is one AI in IEEE that has access to AI information and bylaws and everything. So when you ask it, you're going to get a relevant answer from the IEEE data set. Agents, tools, and workflows. This is important, and large language models are used to build agents that can do multiple things and act. Agents can act autonomously. You give them a target, and they're going to fulfill it. One famous type of agents are the financial market agents, where you ask them to buy or sell at the right time, or given some capital, their target is to make it increase. Safety, robustness, and regulation, these are important. We want AI that has no bias, that is fair and sensitive to cultural differences. We want domain-specific governance. We want sometimes the governments or corporates to govern this AI so that it does things according to bylaws and laws of that entity. We want guardrails and monitoring so that we ensure everything is going fine. These are the 8 major trends. I think now we can take a break before we move from these trends to some of the Arabic national language applications. It is now 11:10, so let's take a break until 11:25. In Jordan, it is 10:25. Hello, good morning again. I hope you hear me. If you don't hear me in the Zoom meeting, please let us know. Hello again. And now as I told you, I'm going to give some information about the Arabic NLP applications that I personally experienced. And I'm going to very quickly go over these problems and how we solve them. The first one is automatic diacritization of Arabic text, followed by Arabic poetry classification and diacritization, then Arabic spelling mistakes correction and translation from the local Jordanian dialect to the standard modern standard Arabic. Let's start with the first problem. This is an important problem. Most of the Arabic text is not diacritized. The short vowels are not added because it takes time for every letter to, when you enter it, to add its diacritics. So usually Arabic text is entered like this, but there are an implicit short vowels or diacritics that are there, but we don't write them. And when we need them, in many cases, we need them. People new to the Arabic language need them in order to properly pronounce words. Also, there are many ambiguities in intertext, but when we add these diacritics, we reduce this. And this is an old Arabic NLP problem, and usually people try to solve it using rule-based approaches, corporas, and the solutions were not perfect. With large diacritization error or large errors in diacritization. In 2014, we noticed the progress in deep learning, and this was the first attempt to automatically add Arabic diacritics using deep learning approaches. These are bidirectional recurrent neural networks. They're better than unidirectional because when you want to predict the diacritic of one letter, you can get better results when you introduce your text twice, from the beginning to the end and from the end to the beginning. Therefore, at one point, when you want to predict it, the previous and next context is known and you get better. So this is bidirectional LSTM. I used the four recurrent neural network layers. The input is the verse without diacritics, and the output are the diacritics of that verse or sentence. With time, we improved the accuracy, and of course, with larger and larger training data set, you get better and better model. And here with 400,000 sequences, training sequences, the diacritization error is about 1.5, which is excellent, and it's much better than previous rule-based techniques. And this is very important. This model that gives this excellent accuracy is only 5.3 million parameters, not billion parameters like the modern large language models, but only with 5.3 million parameters, we can get like an expert level accuracy in diacritizing Arabic text. And what does this mean? This means that this model is able to learn the needed Arabic syntax and grammar, so that and even some semantics, in order to succeed in doing this difficult language task. We've improved on these results using modern large language models. Now we start with some pre-trained large language models like GPT or Google T5, and we refine it or fine-tune it to solve this particular problem. And now with larger models and better error, diacritization error. Arabic poetry is an important branch of for Arabic. Here we are trying to analyze the Arabic poetry verses and classify them into buhur, meters. Also, unfortunately, most of the available Arabic poetry is not diacritized. And when you try to read it without diacritics, it is diacritized. لعمرك ما الرزية فقد مال ولا شاة تموت ولا بعير ولكن الرزية فقد فذ يموت لموته خلق كثير. So the music comes when you properly pronounce the verses, and in order to do it easily, you need the diacritics. Now, this is diacritizing poetry is much harder than diacritizing text because the language is more selected and innovative, and poets usually do things that are not done in normal language. So it's harder to get an accuracy as good as Porse, but this is here we used also recurrent neural networks, 4 layers of bidirectional LSTM layers. But in order to get, this was a breakthrough 3.5, but in order to get it, we used transfer learning, and we complemented this stack. Given the verse, we get the diacritics, but also this is another model. It's trained on larger data that can predict the meter, the class. So this is better trained model with larger data. It learns how to predict the meter, and the meter depends on the sequence of vowelized and unvowelized letters. So it internally predicts this sequence that gives us the bahr or the meter of the verse. But this information is also useful to diacritize the verse. So with this and this, we achieve the highest accuracy. Again, with the smaller models. Same idea was we tried to solve it by large language models, and by just using a large language model, same problem, we get slightly better results. I'm still working on this problem, and I hope that we will be able to improve it soon. This is third problem. There are some common spelling mistakes. related to hamza, to wow at the end of the word, alif at the end of the word, ta marbuta, and ha. And these are examples of common spelling mistakes. Also, it's important to translate Arabic from one dialect to the modern standard Arabic, because the modern standard Arabic is the recognized language. In many venues, you better use modern standard Arabic. So this is from the Jordanian dialect. وين بدك تروح اليوم? In MSA, it is أين ستذهب اليوم? These two problems, correcting spelling mistakes and translating from dialect to MSA, we tackled them with the same project. Here, you can give the text from keyboard or by voice. بدي نام is not MSA dialect, and we developed translation model to translate it to proper language, to MSA, and optionally you can add diacritics. بدي نام، أريد أن أنام، أريد أن أنام. And in order to train these two models, of course, we need training datasets. The current models can do these things, but they're not accurate. So we want to fine-tune large language models to do better job in such tasks. Therefore, we collected from Jordan, from multiple sources like YouTube, scripts, Facebook, and so on. It's split. The dataset is split to training, validation, and test. About 60,000 sentences. Some of them are NMSA, but with mistakes, and some of them are in Jordanian dialect. So the expensive thing, this is fine-tuning, is usually supervised learning. So you give it the input, but you need also to provide the solution. And this is expensive. This is the tool we have developed for Arabic language experts to write the translations of the input sentences that have problem. Now, once you have such data set, then you can tune a large language model to do better in this task. And the results are excellent. Again, with ByteT5 model, which is this large, you can give it something like بإمكاني أنزل لمستواك وأحكي بالطريقة الهمجية اللي بتحكي فيها. This is Jordanian dialect, and it's translated بإمكاني أن أنزل إلى مستواك وأتكلم بالطريقة الهمجية التي تتكلم بها. And as you see, these are example input-output, and they are very good. As a conclusion, I'm going to read this well-written, by the help of ChatGPT, well-written conclusions. Transformers enabled scalable parallel sequence modeling, forming the backbone of modern LLMs across encoder only, decoder only, and encoder-decoder families or types of large language models. The field is now driven by efficiency, concentration on efficiency, like mixture of experts, distillation and quantization, multimodality. We want models that accept the multiple modalities, RAG, retrieval augmented generation, and grounded systems, and agentic workflows with growing emphasis on alignment and safety. Arabic NLP is benefiting directly, as you have seen. We can provide excellent, accurate solutions. For example, we multiple times used ByT5 from Google to achieve strong results on diacritization, correction, and DLSA conversion, showing the value of adapting foundation models to Arabic-specific data and error patterns. Finally, large language models are no longer just larger models. Progress comes from better architectures, efficient deployment, and grounded, domain-adapted applications, especially for Arabic. The slides, all slides are posted on a Google Drive folder, and it's shared with you. Any question? Yes. For the yeah, the question is about the classification, how accurate the classification is. In fact, it reaches 100% when you give the model multiple verses, because sometimes for one verse there is some ambiguity or some allowed meter variations that the poet does, and make sometimes the meter may look like the verse may look like in another meter. But when you feed the model with multiple verses, then the accuracy approaches 100. For a single verse, the model is slightly better than 97%. The accuracy is about 97%. No. Okay, let me go back. Okay, now this is وأمطرت لؤلؤا. These verses are from the vertical Arabic poetry branch, and there are 16 meters in الشعر العمودي, and the model can classify an input verse among these 17, and also can detect when the text is porous, is nafir. So the model was trained on 17, not 16, 17 classes, including the porous nafir class. Is there something on the chat? Yeah, how long have you been working this, Professor? I've about 25 years ago, I've started working on problems related to the Arabic language. I've started on OCR, optical character recognition of printed, then handwritten Arabic text, and with time I moved to other things like diacritization, error correction, and poetry. Okay, now to the third and final part of this workshop, which is with this title, Working with Large Language Models. Okay, I want to change the view again. Okay. In this final part of the workshop, I'll start with some more specific information about training and interfacing with large language models. Then more information about tokens and embeddings and how these are done with modern large language models. Then we go to the three exercises, one to generate text, the next one for text classification. In fact, it is sentiment analysis. And finally, building a model or using a model that translates from English to Arabic. In these labs, I'm going to give some theory, some introduction to the used libraries and tools. Then you go to Google Colab to play with some script and modify it to get other things. The reference for these labs and exercises and even the figures in this slide set come from this excellent book, Hands-on Large Language Models. Okay, training large language models. You know that large language models are usually pre-trained on unsupervised data. This is called, again, self-supervised learning, where you easily get from unsupervised data data that can be used for training. You bring many text sequences, and you either ask the model to predict, you give it the start and you ask it to predict the next word, or you give it some sequence and you hide some words, and the model must predict the missing words or tokens. And with time, the model is going to build inside it language model. It'll build inside it the rules and ability to understand text in that language. This is called pre-training. You get the base large language model, and usually the developer or us, we do fine-tuning. Here, fine-tuning like correcting spelling mistakes is usually a supervised training task. The model already knows Arabic, for example, but we train it further to be better in translating or translating text with spelling mistakes into better text. And at the end, you get a fine-tuned large language model that without target, without label, you just give it the input and it predicts the correct output. There are, as you know, open models, and there are proprietary private models done by large companies. Here, when you have an open model, you usually host it on your machines, you download it, and the user use it on your user hardware to get answers. But also, you can build applications that interface with proprietary large language models. For example, OpenAI provides API that allows you to, from your programs, from your applications, to send a question to some large language model hosted by OpenAI, and you get the answer over the internet. The book, the reference, teach you how to do both. Now, tokens and embeddings. You already know that for an input text, like have the parts who preceded, is usually split, is tokenized. There is tokenization step where it is split into tokens. Tokens can be words or smaller. And usually there is an embedding step. The tokens, each token is converted to some representation. This is called embedding, where these embeddings are much more useful for the model. And they are rich descriptions or representations of the tokens. This is an example. Here we have a model that has a tokenizer, and this tokenizer takes any text and identify about 50,000 tokens. So number of tokens are usually limited. So there can be some tokens that are out of vocabulary. So better tokenizers have larger and larger number of tokens. And each token has an ID, and in embedding, we convert the ID of the token into some real vector that represent that token. Here we have this example. It seems that for this tokenizer, have the parts. Parts is not a known token, but it is split into B and arts to two tokens. And as you see, each token has a token ID. And these token IDs are given to the language model. This is multiple types of tokenization. This is word tokenization, where the sentence is split into words, and every word is one token. But there are, as here, there are sub-word tokens, like here, bard is split into bard and S, because S is used for plurals. And preceded is split into two, precede and ed. There are also models that does tokenization into characters. The split is split into characters. And even there are models that split the input into bytes. For example, okay, when you use Unicode and UTF-8 encoding, the English letters and many punctuation marks are represented using 1 byte. But for other languages and things, you may need more bytes. For example, for Arabic letters and diacritics, you need 2 bytes for 1 Arabic letter. And there are even cases like this musical sign. Here you see that you need 4 bytes in order to encode this single symbol. By the way, byte 5, which we heavily use in in our Arabic research, is from by by comes from byte. It uses the tokenization is at the byte level. Now, the second step the second step is token embeddings, and this can be done in multiple ways. You can create word embeddings separately by using some simple neural area network. And also you can find word embeddings as part of the process of pre-training a large language model. Here I'm showing the word to vector technique to get excellent word embeddings. And there are 2 techniques. One of them is continuous bag of words. The idea is you present, it's similar to self-supervised learning. You present some sentence, you hide 1 word at a time, and you train your model to predict the missing word. In order to succeed in this, the model is going to, here we have n hidden neurons. Let's say that there are 1,000. For every token ID, you're going to get 1,000 weights for that token, connecting it with the hidden neurons. And with time, the model learns excellent representation of each token. Therefore, when you take these learned weights, this becomes the embeddings of every token. A skipgram is the other way around. You present 1 word to predict the surrounding word. Okay, now embedding, this slide is about embeddings processing in large language model. You know the step of the tokenization. Here we have 5 tokens. Then the step of embeddings, and here we have 5 vectors. Each is 1 embedding of 1 token. Then your language model works on these embeddings, and basically what it does through layers and layers of feed forward networks, attention, and so on, it finds the relationship and provides better representation of the input in an output representation that takes into consideration the order and the context of every token. I would like to mention that there is multiple types of embedding. I'm going to start from here. There is the token embedding, one token, one vector. But also, maybe you have here vocalization is split to two tokens, but you can develop models that gives embeddings based on word. And also there are models that, given multiple tokens or some input, some sentence or paragraph, some text, some sentence here, it gives you one vector that describes this entire sentence. And even there is, you can feed some models an entire document, and you get an embedding that describes that entire document. And this is useful for search and categorization purposes. Yes?
Where you use, for down the bottom of the, you need to use the embedding vector, right? Here to see a little bit.
Yes and no. Yeah, I know that some token embeddings are in thousands of elements, and you can get excellent document embeddings with fewer than that. So it's not embedding size does not increase when you move in this direction. But the model's power usually increases with larger and larger embeddings. Okay, because there is some noise, I don't hear you. So
I'm asking that what's the difference between these embeddings? Will it give us the different information or different accuracy? Or
yes, yes. The question is what are the differences between all these four types of embeddings? These multiple types of embeddings were developed to address multiple application areas. So usually for models, language models, they internally use token embeddings and maybe Word documents. But when your interest is to analyze one sentence, like when the sentence is an answer to a certain question, or when a sentence is a question and there is another question, you want to find the similarity between these two sentences, two questions, then you can get excellent results when you do sentence embedding. You embed this sentence and embed this sentence, and you can then find the similarity, because if two questions ask about the same thing, then you can provide to the second the answer of the first. This is the area of question answering. For document embeddings, it's used when you want to retrieve data, when you want to store and retrieve documents according to some search. And here, when the document is described by embeddings, we don't search by whether some words are there or not. Usually these embeddings are topic embeddings, so you can find relevant documents from their embeddings, even when they don't have some keywords, some main keywords. So this is a semantic search. Okay, now I'm going to show you now some code we usually use when we deal with large language models, when we do tokenization, and when we do embeddings. Okay, so here transformers. This is very powerful library from Hugging Face. It's difficult to avoid it. It is difficult to avoid it. Here we are importing some class for auto-tokenizers and another one for large language models. And here we want to use an open source model from Microsoft. It is the Phi 3, some variant of the Phi 3 pre-trained large language. So this is the model ID, and we use auto-tokenizer from pre-trained. We give it this model to get its tokenizer, because each model understands some tokens, and there is one-to-one correspondence between tokenizer and the model. Therefore, for some model, we get its tokenizer. Assuming that we want to tokenize text, now after doing the tokenizer using the tokenize function, we give it the text and we get the tokens. The tokens, this is the list of tokens, and you see that internally hello is hello with underscore. Phi is split into two tokens, PH and I. This character is one token, 3 is another token, and the exclamation mark is number 6. Now, each token has an ID, and we can encode the text into token IDs. And as you see, the IDs are integers from 0 up to some large number, depending on the number of tokens that this tokenizer supports. Now, going to the embedding step, here we get from this model, again, from this model, we want to get it using this class from transformers, Hugging Face transformer. So when you execute this, it may take some time, especially when it is the first execution of this code, because your code must go to some repository and download the model. So it takes time, but we get the model. Now you can use, we're going to use later the entire model for doing interesting things, but you can only concentrate on the input embeddings layer. And here I'm getting the embedding layer of this model, so that when I give it the token IDs, the input IDs, it should give me the embeddings of these tokens. And then I get embeddings. You can inspect the shape of these embeddings. And here we see 1, 2, 3 dimensions. The first one is because these models usually accept batches. My batch here is one sentence. Therefore, there is in the batch one input sentence, 6 tokens. This one has 6 tokens, and each token has a vector, embedding vector of 3072, very huge. Each token is represented using this long embedding vector. Here we can display the first 3 numbers from the first sentence, the first token, the first 3 the 3 elements of this vector. And as you see, these are real numbers, positive and negative numbers. Of course, we as humans, we don't understand what's the significance of each one. But sometimes when you inspect multiple similar names like Muhammad, Omar, John, and so on, these are all male names. Usually you can see some similarity in some places in this vector, indicating that that these are all names and male names and so on. Okay, now this is the introduction. I hope now you can start playing with talk. We're going to, the first lab is about generating text. And we want to use a large language model to generate jokes. We will do it using a pre-trained large language model from Meta, the 5.3 Mini, and it's available on Hugging Face. This model has 3.8 billion parameters. It's considered lightweight. It's state-of-the-art open model trained with the 5.3 dataset that includes both synthetic data and filtered, publicly available websites data with a focus on high quality and reasoning dense properties. The model belongs to the 5.3 family and supports 4 token. This is not bad, 4K token context. So your prompt and the history can be up to 4K long. Okay, so again, we use from transformers auto model for casual large language model. And we also need the tokenizer, the auto tokenizer. Here we get a pre-trained model using this transformer class. Here I'm specifying the particular model that I want to download. And see, this is like always, here the group or the company slash the model name that you want to use. We want to use CUDA, we want to use GPU so that the execution time is reasonable. You can put here true or false, but let's use these inputs. Also, we need the tokenizer because we have text and we want to tokenize it. And as you see, we get the tokenizer of the same model. We get this tokenizer of the same model. I said that this is to use NVIDIA GPU, and then this is a usual step when for large language models, instead of calling like tokenizer, embedder, then the model, we put the steps in one pipeline. And here we're using pipeline from transformers. We're creating pipeline called generator because our intention is to generate text. This is for documentation, text generation. We give it the model and the tokenizer. So this is a model. This is a pipeline that will do tokenization followed by running the language model. Okay. Here, return full text is false. We don't want it to return everything, including what we've given it. We only want to get the model output, not the prompt. Also, we don't want very long output. We can specify that the maximum output from the model not to exceed 500 tokens. Do sample here is set to false for repeatability. Models can generate multiple output for the same prompt. But when you do sample false, the model is going to give you not a random answer, but it's going to give you, for the same prompt, it's going to give you the same output. Now, we need to create the prompt. And here, the prompt that we will give to the model, so the model is going to generate text. Here, we are specifying that this message, which is asking the model to create a funny joke about chicken, comes from the user. User is the one providing the prompt. Okay, and because generator is the pipeline, we've done it in the previous slide. So when you give it this message, you're going to get an output. The output is tensor batch of one entry. Therefore, from the output, we take the first entry, which is a single entry, and we index the generated text to get the generated text from the model. And this is the lame joke. Why did the chicken join the band? And the question, this is the response to this prompt because it had the drumsticks. Okay. Now, okay, I hope now this code is available. Now you're going to to start from this code that I've presented in the previous slides. It's available on a notebook by the author. You open the notebook of chapter 1, generate a joke about chicken. I'll come back, but let's do it one step at a time. Okay. This is the model. This is the repository, book repository. Go down to the notebook of chapter 1. Notebook of chapter 1. Then you find the notebook for generating text using Phi3. This is the notebook. And you see here that the first cell, you need to execute it to install the transformers package from Hugging Face. So you execute it. It takes some time, then check the next code cell, execute it, and so on until you get your joke. So I'll give you some time now to do this step. Yeah, it's good. Here it's downloading the files needed for the model, to get the model from Hugging Face. If you face any problem, please raise your hand.
Is it only generating like one joke, or
Yes.
what is this output 0? Is it the first one, or
No, this is for this prompt. There is only one prompt. There is only one output. So so there is nothing else that you can expect.
if I wanted to like make a new joke, do I change the prompt or better?
Okay, now try to change this and rerun it from true to false, from false to true. It has changed. Now you can ask it another thing, like it can tell stories or other things. You can change the prompt. This is the prompt. You can change it and ask it another thing, and you're going to get a different result.
So it's only like 500 tokens max.
Yes. Now, it keeps generating when you run it multiple times, it keeps generating these same chicken joke. How to make it give us other jokes? Temperature, or here, do sample. When we do sample, do sample here is false. It does not do sampling. But when we write true, it's going to do sampling, not always give us the most probable generated text, but sometimes give us the next or maybe the next most probable text to generate. So here, when I run it again, run this cell and this cell again, I get, oh, it's the same joke now. Oh, yeah, let's try another time. Now it has changed. It has given me a different joke. Why did the chicken join the football team? Because it wanted to be part of the co-op. Okay, now can you ask it to do something else other than giving chicken jokes? How? Change the prompt. Yes. I want to ask it again. I like chicken. Give me a short story about chicken. And you just change the prompt. Now it's thinking longer because it's going to generate longer text. The jokes are short usually, but even short stories are longer than jokes. So it's crunching, and now we get this small story about chicken. Okay, so this is the lab. Play with it, and I'd like to take another break. Okay, any question, any concern before the break? Okay, so let's take a break. Yes, go ahead. Question. 9.
So here in the multi-hop vectors, the zero represents the missing point. The input.
No, I'd like to change something here. Okay. Okay, the question is?
Yeah, so the multi-hop vector represents like if the word is missing from. So one means that the word is there.
Yes, yes, yes. Here, Claude Monet painted the Grand in 1806. So here, painted, this token is not presented. And the model, it seems, is effective in predicting that. Now it's trained, and it's predicting with high probability that the masked word is painted. Yes, here you can mask not only one word per input, but you can speed up your training with masking multiple words in each training instance.
And why is it not predicting 18? Or is it because it is just like the task is to just predict single word?
Okay. Maybe this is typo. Why this is too low? Maybe this is typo. Maybe at another time step, we're going to get it here. Hello again, and welcome to the final part of this workshop. We have two more labs. We've already seen the generating text lab. Here we used large language model in order to generate text. So you give it a prompt and you're going to get some response, and this response is not bad at all. You get jokes, you get short stories, and it is not a bad model at all. So of course, when you use larger models, you're going to get even better responses. But for this model, you were able to run this model on Google Colab. It has limited memory, but for larger models, Colab is not sufficient. You need to go to better cloud services, or use a workstation with large memory and powerful GPU. The next lab is about text classification. I'm going to talk about text classification using large language models. Then we're going to see code and try it and modify it. We can use representation language models. These are encoder only, and also we can use generative language models like decoder only. And we can use representation models given some text input to get some class. Like the classes can be 0, 1, or 2, and here we're getting 1 for this particular input. Also, you can use generative models, and in this case, you ask it to generate the result. You tell it, this is the input sentence. Please generate the output in this format. Give me 0 when it is like negative, give me 1 when it's neutral, and give me 2 when it is positive. You can use both representation and generative models to do classification. Now, this is more detail about text classification using representation models. We can this is BERT. BERT is representation model, encoder only architecture. We can use it to get directly classification or to get embeddings to describe the text in some powerful representation. Here we get task-specific model that is able to do classification, but here we only get embeddings, which are powerful representation of the input text. For the task-specific model, for the classification model, you directly get the answer. But for the one that gives embeddings, then you need a way to convert these embeddings into class. And here you can use classical machine learning techniques like logistic regression, which is the simplest classifier. So that from embeddings we get 1. Okay, in our lab, we're going to use a task-specific model, a model that directly gives the class. And the input is, as usual, text like her vocalization was melodic. This is a positive input, and the output here is one indicating that the sentiment or the class is positive. Usually, as usual, we need tokenization. This text is split into tokens. The token IDs are presented to the models so that the output is the class. We're going to play with sentiment of movie reviews, and we want to classify movie reviews into positive and negative. This is very famous dataset, the Rotten Tomatoes dataset. There are about 5,000 positive comments or entries and equal number of negative entries. So it is balanced. For the task-specific model, we're going to use some BERT model, the Roberta model, which is derived from the BERT architecture introduced by Intel several years ago. Also, this is available on Hugging Face, so we're going to use the Transformers library to get this model and use it to find the sentiments of reviews and classify them into negative and positive. Okay, so here datasets is also from Hugging Face, and there is this function for loading the datasets available on Hugging Face. Rotten Tomatoes is data. Now, when you type data, you're going to find that this dataset, this is the dictionary that describes the dataset. It's already split into train, validation, and test. And usually we train on train and test on tests. And for some training algorithms, we iteratively test on the validation set. Now, once data is loaded, we can inspect some entries like some of the train entries. And here we are inspecting the text of the first entry and the text of the last entry. So in the train subset, the first one, the rock is destined to be the 21st century's new Conan. This is Conan was successful maybe in the 1980s. This is successful movie from the 1980s, and The Rock is more recent actor. And notice that the label here is 1 for The Rock, but for the last entry in the train subset, concentrate on this part of the review. The movie is all portent and no content. So this is obviously a negative review. So this is labeled data set. There are inputs and reference targets. We want to build a pipeline from the Transformers library, and this is Roberta from Cardiff NLP. This particular model is tuned for sentiment. This is general model, but it's tuned for sentiment analysis. Here we build the pipeline. We want the model and the tokenizer associated with this model. Return all scores true. It's going to return all scores. This is not 100% what we want. This model has 0, 1, and 2, negative, neutral, and positive. But we are only interested in positive, in classifying into, sorry, negative and positive. return all scores, and then we'll analyze them. And the device is CUDA. On Colab, there is CUDA, and you need to make sure that you select it before running such programs. The third step is that we want to test how good this model on the test set of Rotten Tomatoes. So here I'm using TQDM. This is a function that shows progress bar on the display. Because remember that the test set has more than 1,000 entries. The model is going some time to analyze them, so we want some progress bar to show the progress. So here we have for loop. The for loop is going to operate on this more than 1,000 test set. Here another helper function, another helper class. It can select the needed particular field and give it to the model. So the key data set will take from the test set the text field. We don't want to give it the question and answer, the input and answer. We only want to give the model the text. And for the progress bar to operate, it needs to know the total number of items in the test set. So we're going to get one classification at a time. And here, I told you that there are, this model gives 3 classes. In fact, it gives, its output has 3 neurons. 0 is negative, 1 is neutral, and 2 is the positive review. And all these are probabilities. Like here, maybe 0.1, here 0.15, and here will be 0.85. And when we need to inspect these probabilities to select one of these 3 classes. And this is done. So we start by getting the positive score, then the negative score, and we use the NumPy argmax in order either to get 0 or to get 1. When the negative score is higher, we get 0. When the positive score is higher, we get 1. So by this, we have converted probabilities of 3 numbers into 1 number that indicates the class. And now here with assignment, we append assignments into the Y predicted list. And now here it's a list of 0s and 1s. And this is compatible with Rotten Tomatoes dataset, because Rotten Tomatoes dataset, we have 0 and 1 as labels for the classes. And that's it. Now you have, at the end of this, you're going to have here more than 1,000 label or predicted class for the test data set. You can inspect them individually, but usually in scikit-learn, which is very famous and powerful library for machine learning, there is a function called classification report, and you give it the true expected data and the predicted data, and it generates this report, which is very useful because here, for example, you get the accuracy when comparing the reference with the predicted. You get the accuracy over 1,000 cases. Okay, so this code is provided to you, and to play with it, you go to the same repository of this book, open the notebook of chapter 4, run the code cells one at a time, so that you get this report, and you should get an accuracy of 80%. After that, I'd like you to modify the notebook, the code on the notebook. We're interested in Rotten Tomatoes anymore. We want to classify these 3 sentences. I like this workshop. Is this positive or negative? Positive. I don't like this workshop. Negative. I have not decided about this workshop yet. This is hopefully the machine is going to classify it into neutral. So let's test it. I've invented these 3 sentences, and I hope that the machine will be able to classify them into 0, 2, and 1. This is 0. This should be 0. This is the Roberta classifies into 3 classes. Sorry. 0, 2, and 1. So you, as before, you go to the repository on GitHub. Now we go to chapter 4. And start executing cells from the beginning. We need to install from the transformers, sentence transformers from OpenAI and datasets. Okay, the second code cell is for the data, for getting the data. For getting Rotten Tomatoes dataset. And as you see, this data set is split to train, validation, and test. And this is the first and last reviews. Now here, it's going to take time because we want to load this model, Roberta model. Yes.
The criteria.
Roberta is a general representation model, but some of this model was fine-tuned for multiple other functions, multiple specific tasks, including a classification into these three classes.
Two words which have same meaning. How it's
It does classify just words. It classifies the sentence and the sentiment of the sentence.
yeah. So like if there's two sentences which mean same but written in a different meaning, right?
Yeah, it depending on its statistical parameters, or the parameters that they've learned from statistical machine learning, it's going to give some meaning. Sometimes this is correct and sometimes it is not. And this is why we don't get 100% accuracy. The accuracy is 80% because sometimes it's.
So and also the model, the training of model, it also depends on that, right? Like you have to get the accuracy and precision up. So
Yes.
you need to train it and like give the synonyms.
Yes. Now,
Just detect it.
Roberta is a small model, fine-tuned on relatively small, fine-tuned for this task, and we get 80%. But if you go to a larger model, like maybe you can use even ChatGPT to do it, you're going to get better accuracy, higher than 80%, like 87%.
Right.
You're welcome. So it's done. Yes. Now, we want to run the model on the test set. Notice the progress bar out of 1066, halfway there. Now finished 100%. Then we use the classification reports from scikit-learn, and we get this accuracy of 80%. Now, it works for me. I hope that it works for you also. But now we don't want to do this part. We don't want to do this part. We want to give it our own data. Here, these 3 sentences, and you can put them this way. Here, this is a list of 3 items. You can give the model this list of 3 items, and the model is going to return 3 answers. Try it.
I like workshop positive sentences should have the value 2 and negative sentences should have this space here. 2 is positive.
Yes. So I don't know. Okay. Yes, this is a mistake because the second one, this is a mistake. This is 2, right? And this is 0, and this is 1. Because the second one is negative, and negative is 0. Thank you.
It doesn't classify like that.
Huh? Do you get the answer? Okay.
I think yeah, this is classified as the perform maybe it's much.
Text. Yeah, it does not last much, but it's giving you the right answer. Okay, good.
How do I go on all this? About my data, the pipeline.
Now, you just give the pipeline. No, here, you just give the pipe the texts, your
Yeah,
text.
I gave the text and length of text, and then
Yes,
do I just print like vibrate? So it's 1 0 1 0.
yes.
How is that? It's
So it is
neutral and then negative, right? Both are negative. Or I don't like that. Well, it should be like 2 2 0 and 1, right?
please print the shape of Y predict. Because it is list, so length of list. Okay. Three. Okay, let's see what's the difference.
I got 1 0.
You get what?
Like
Like him? Okay. because the result is not a simple answer. The result is a tensor that has 3 numbers, and you need to select the largest number, argmax.
So what if I remove argmax?
Huh?
What if I remove argmax and then it just shows me like what's the percentage it's
No, no, we don't want, there is also neutral. And now we don't want to ignore the neutral case. So, sorry. So get also the neutral output, the neutral score. Which is 1, yes. And add it here.
$102.
Yes.
But then it's upside. It says this is positive. That's negative. That's neutral, and this is negative.
Yeah, but here you're not using, you don't need the for loop. You're calling the pipe once without helper function to work on one thing at a time. You're working on them at the same time. I'm going to show my code. Okay. I'm going to add a new cell and put in it my code. Oh, it's not clean. Now, here is the list of text I give in my solution. The list of 3 text to the pipe, and I get 3 outputs. Here I work on the texts and outputs and get the max of the scores. Let me execute it. So the important thing is you get for each text 3 values. So there are 3 inputs, and there are 3 scores, and each score has a label and a score. So you need to zoom in to these 3 numbers for every task and find the argmax of the so that to get the class. So the first text, I don't like this workshop is negative because, and the negative score is high. The second one I have not predicted. Oh, the first one is I like this, and this is positive. The second one is negative, and the third one is neutral. I'm going to share this code with you on the chat. Control A. And I hope it is clean enough on the chat so that you can copy it, execute it, and understand how it works. Can you easily copy from the chat to your notebook? Shall we move to the third one? Do you need more time? Okay. Now, the third one is about translation. Here we're going to, we don't know how to work. We're going to start not from given code. Here we're going to build everything from scratch. Hugging Face Hub is very important in modern machine learning. We're going to visit Hugging Face hub. We're going to navigate to documentation related to the translation task. Then we're going to get some code there. We're going to read and get some code, so some code, so that we use it for our translation task. Initially, we're going to use this particular model, the Helsinki. I'm not able to see my cursor. Okay. Initially, we're going to use this Helsinki NLP Opus machine translation from English to Arabic to translate I miss you to Arabic. This is a small model, and you'll see whether it'll give you a good translation or not. So the procedure is like this. You go to Hugging Face hub. Here at the top, there are docs. You go to docs, and you want to learn about the task of translation. Therefore, you go to the tasks section, and in this tasks section, search for translation. And translation is here. Under natural language processing, there is translation. And this is some tutorial how to use the transformers library to do the translation task. There is a video, you can watch it, short video, and this, let me enlarge it. Here you can ask you can create a pipeline with the default built-in options to do translation from English to French. This is what not we want. We want something like this. We want to specify our model and build a pipeline that uses the specified model in order to do the translation task. Then you can, once you create your translator pipeline, you can translate English to Arabic. But of course, you need to change this one from French to Arabic, from English, not French, to Arabic. So to do this, you need to create a collab, a new collab. Now, the default collab setting does not use GPU. So here at runtime, you go to change runtime type, and instead of CPU, select T4 GPU. We want a GPU. I think this is a medium scale or medium level GPU with 8 GB of video memory. This one can run the models that the default models and the Opus model from Helsinki. So save it. Now, this is the code we want. Take this code, put it in your notebook, Colab notebook, change it, and run it. Did you finish it? Mhm. Is this good translation? No, it's not.
Or how are you mean with the diacritics?
No, no. Enter I miss you.
Oh, I miss you. Okay.
Okay. For how are you, it's okay. For how are you, it's doing fine. But we wanted to translate I miss you. So you need to change this part into I miss you. Is it okay? No? Is it good translation?
Like,
Do you speak Arabic?
yeah, I speak Arabic.
Okay. Is it?
It's the first one, this one, أنا أشتاق إليك. I put an exclamation mark
Okay, without exclamation mark.
without, when I put a dot. مش عارف. أتغيب عن
أتغيب عنك is bad because it's not أتغيب عنك أتغيب عنك means not I miss you, I will be away from you.
Yeah, something like this.
So,
You don't understand the context. Put in a different.
no, it is a small model and not that powerful.
Yeah.
So the translation quality is not that good. So when we execute it, we get, as you see here, we get I miss you. No, let me try run it again.
I think you changed the comment, change the translation. You.
Yes. Now it's translating, it's crunch. أتغيب عنك is not a good translation because أتغيب عنك means I will be away, something like that. I will be away from you. But this is not I miss you. Now, shall we move on to a better translator? Yes. Yes. Now I intentionally used dot to reduce the amount of hints I give to the model. But when you put the when you put the exclamation mark, you've tried it this way and you get better translation. أنا أشتاق إليك. This is very good translation of to Arabic of I miss you. But please don't give this hint to the model, keep using the dot, but we want to search for a better model. Yes.
For the common, for the full stop location, on the other side, why is it not at the end of the part?
Here, this is presentation issue. The Google Colab thinks that the dot is coming back to English text, so it puts it after the Arabic. But when you inspect one character at a time, dot will be at the end. Yes. When the exclamation mark is given to the model, it will do better. But we don't want to give it this hint so that we search for a model that is more powerful.
Why does it do that?
Because usually when you use a dot, then this is some statement, informative statement. But when you put something like this is more related to emotions, and this is a hint to the model that you are in the emotion side, and the better translation is أشتاق إليك. Okay, now we have another part. This is the straightforward translation using the model suggested in Hugging Face. We want to use better model. And now we're going to search for the suggested model is straightforward with the 3 lines of code. You get it and you build it. But there are other models that sometimes harder to deal with. And some of them are much better and are popular. So we will go to Hugging Face again. We will search the available models on Hugging Face and search. There are filters that we can use to refine our search to zoom in on the models that can do translation between English and Arabic, and we're going to sort them by popularity, by the number of downloads, so that we get the most popular at the top, the most popular models for this problem. So I'm going back again to Hugging Face, and my suggestion is you go to models. There are many models, and here I'm going to zoom in to or refine my search for those models under machine learning that are able to do translation. Without zooming in here, look, there are about 2.5 million models on Hugging Face. Now let's refine to translation, and now there are only about 8,000 models that can do translation. Go to languages and select English and Arabic. Now there are 451 that can do Arabic and English. Sort them by most downloads. This is popularity. And now you get the most popular models that can do this thing. You cannot just take this name and use it instead of the Helsinki model, because they are a little bit different. You can select the first one, but this is 8 billion parameter. And I know that it is large. And I know that this model it's good, but it will not, Colab does not support it. When you run it, it's going to break. From Facebook, this distilled model is distilled from a 600. I don't remember whether the 600 is the distilled model or the original model, but anyway, it is not in the billions, it is in the millions. This one may work. Now, the procedure is like this. Select one of the top models. Be careful, very large models may not fit Colab memory. I always use currently I always use generative AI to get code. So I suggest that use your preferred generative AI tool with the following prompt. Tell it, using the transformers package from Hugging Face, generate Python code to translate the sentence, "How are you?" into Arabic using the model, and here give it the model name that you have selected. You're going to get some code. Hopefully, when you copy it and paste it into Colab, it will work. What do you use to generate code? ChatGPT or something else? ChatGPT is excellent. Gemini also gives decent code. I told you that I'm currently using long context in my research to get script to do things, and also to get better results. I now think of ChatGPT not as a tool. I think of ChatGPT as an expert colleague that is very skillful in coding and analyzing data, and this colleague is I can discuss with this colleague things like I want to achieve this thing because I know what I want. I want to achieve this thing, but I don't know how. Please tell me what is the best technique to do this and that. And it's expert. It knows many things, and it helps me achieve the results I want. So here, ChatGPT can be very useful. You give it this prompt, it gives you the required code, and you can have follow-ups with ChatGPT in order to keep improving your code into better and better versions until you reach some production version of your code that can be used in real applications. So, did you reach anything?
Yeah, I got it.
This is the code. And this is better, right?
Yeah.
Right? Okay. Okay. So, w- did you reach?
No.
Mhm. Now, which model is it? Facebook model? And this code is from Google, from ChatGPT? Gemini. Okay, let's see. He used ChatGPT and works. This is okay. Sentence to translate. How are you? Not how are you. We want I miss you.
But it gives me the answer in English.
Yeah. So tell Gemini that he has made some mistake and it's not translating to Arabic. We will, Gemini will think further and
So we give that prompt to Gemini?
yes, using the transformer package, yeah, from there to selected model and put in place of the selected model, the Facebook model. Yes. Change this one to I miss you later, once it's done. Is this, did you get this from ChatGPT?
That's from Robert and Gemini.
Okay. I hope that it works. I did not use it this way. I brought longer code for ChatGPT.
Oh.
No, this is Helsinki.
Yeah.
This is 10 cent. Is it the first hit?
Yeah.
I hope that it works because this is a large model. Maybe after
I tried to change it.
yes. Wait, but you may get out of memory message. So is it?
It's giving me like an attribute error because it's making something up. So I'm like, oh, it works.
Now, for how are you? It gives you كيف حالك. Change it to I missed you. Dot. Yes, this is excellent. In fact, this is better than أشتاق إليك. How are you doing? You have error?
Yeah, actually, I think I with this as this transformer.
Okay.
And
Is this a popular transformer?
no, not popular one.
What did you select?
But I went for the very less parameters, so
Okay.
I just went with this.
Did you give it to ChatGPT and you get the code from ChatGPT? But when you run it, you get some error. Now, either ask the AI in Colab to fix it or ask ChatGPT to fix
Yeah,
the
that's
problem.
what I did right now.
Yes,
And I'm just running.
you're still getting. So there is, it seems that there is tokenizer mismatch problem.
Yes.
So I'm going to take this prompt and go to ChatGPT. And I'll ask it to, I'm copying this Facebook model. Now Facebook is giving me this code. ChatGPT is giving me this code. I've copied it and back to the Colab. I'll paste it here. I'm going to change the sentence. I'm going to change text to I miss you. Of course, it needs to download the model. Okay, it has finished. And the translation here is أفتقدك. Now we've seen سأتغيب عنك, أنا أشتاق إليك, or something like that, and أفتقدك. Which is the best translation? It is this one, أفتقدك, because it is a direct translation of I miss you. Okay. uh, yeah, to conclude, we've learned few things in this workshop. After the introduction to NLP, we learned about the large language models and how their architectures and their applications. And I've shared some of my experiences related to solving problems related to Arabic NLP. And the last part was hands-on large language models, mainly using Hugging Face models and the Transformers library. As I said, there are excellent resources. ChatGPT and other generative AI are excellent in generating code and solving NLP problems. But for basics, I strongly suggest the hands-on large language models textbook by Al-A'mar. So that's it. And I hope that you've benefited from this workshop. Thank you for coming. And again, thank you, Ariel, and thank you thanks to your club and the department. Thank you, and I hope that you enjoy the rest of your weekend. مع السلامة. For the friends on Zoom, have a nice day, and thank you for joining. مع السلامة. السلام عليكم.